One thing that I will say about the search for quantum gravity in general is that mathematical physicists and theoretical physicists seem to very much want it to be some kind of perfect, beautiful, abstract sort of deeply mathematical idea that fails to account for all the fuzziness, messiness, quantum disorder, and the just general diversity of gravitational conditions in which we find in nature. And I think this is best exemplified in B.L. Hoo's work on stochastic gravity, and this idea that it's quite plausible, I think, to have this notion of a microscopic theory of gravity, whereas general relativity remains the hydrodynamic theory of gravity. And I think that B.L. Hoo was very right to have pointed out that, and that gravity most likely arises as a result of constant vacuum fluctuation, constant quantum fluctuation in the background. That must play a huge role in gravity as we understand it by Einstein's field equations, because we have things like the cosmological constant in Einstein's field equations. So therefore, we've got to have a kind of a vacuum, which is one way or another emitting energy, right? So the way that we currently think that this happens in the standard model of particle physics is that we have the creation and annihilation of particle-antiparticle pairs, and I've in my own work put a bit of a different spin on this and removed this necessity for particle-antiparticle pairs by merely having tunneling electrons in the background. And this simplifies everything a lot in my opinion, and this gets rid of our need for, well, antimatter possibly in its entirety. I mean, we don't know yet. I mean, we detected antimatter many times in our detectors, but I think that that could just be different ensembles of the gauge bosons masquerading as different particles of matter, or different particles of energy, really, I should say, for bosons. But yeah, what we had to deal with, what we're confronted with, say in black hole firewalls, with this confluence between general relativity and quantum theory. And it's particularly, I think, a fault on the part of general relativity, but it's so much like this, that general relativity expects these smooth curves of gravitational field, but when we look at nature, that's not at all what we see really. We don't actually see much gravity. Well, we don't see the smooth curvature of space time around black holes very often. What we see is a huge, great firewall, this great, pulsing area around a black hole that is full of trapped radiation, trapped gas, dust, rock particles, everything else. And light entering it gets trapped by all this stuff and slowed down, if you like, instead of the length being contracted, I think, very much. But I mean, of course, the light is still moving at the speed of light, if for no other reason than that black holes rotate at the speed of light. So it's moving in an angular way, in that sort of way still. And we do observe regions of space that do seem to be being curved by gravity. However, as in these cases of Einstein rings, these annular structures that we find around very dense galaxies, and the light shining from a galaxy behind that galaxy creates the Einstein ring. I think what's going on in those cases is that there's an electron density, and that the electron density is the gravitational field of the object, and that light is getting trapped in that electron density and escaping in this sort of curved pattern that looks very beautiful and seems to provide excellent evidence for Einstein's theory of general relativity that space-time is indeed curved. But really though, it appears to be curved. It's just an illusion, really. And that's concomitant with something that Einstein said about reality is just being just an illusion, albeit a very persistent one. I believe that is the truth still, and that there's something deeper going on. There's always something deeper going on, and what I've managed to, I think, arrive at in my own work on quantum gravity may not even really be a scientific kind of idea. It may be more within the ken of philosophy, so to speak. It might be more like a syncretism of the varying different major theoretical approaches to quantum gravity that integrate those with various other smaller ideas into something that's reasonably presentable. That's more like a diagrammatized popular representation of the idea that explains physics, cosmology, etc., and does so within reasonable rational bounds and it is more like a philosophy of the whole thing, or a philosophy of all nature. Because when it gets to the force of gravity and its varying manifestations in nature, particularly when you talk about quantum gravity, I mean, really, what is the difference between a theory of quantum gravity and a theory of everything anyway? Because a theory of quantum gravity, I mean, you've got to integrate that with the other three fundamental forces of nature: the strong and weak nuclear force, and the force of electromagnetism. I think that the forces of the strong and weak nuclear forces are deeply electromagnetic anyway, of course, and it's not as if the charge of the electron and the charge of the proton in the hydrogen atom have no role in keeping the electron stable around a hydrogen atom. Or it's not really stable, it's a lot more complicated than that, obviously, but yeah, it's like, this on my arm, this hydrogen atom here, like this negatively charged electron, this positively charged nucleus, a positive and a negative charge going together. That is, of course, the electrical force. That is, of course, the force of electromagnetism. But somehow we need to get from this picture to incorporate everything around it. And this is proving a bit trickier, and we need to sort of figure out, what this gap in the middle is caused by. I think it's caused by the cosmological constant, by radiation pressure, and that would be a theory of what we would refer to as dark energy then. And this is really like, these philosophical considerations, I think, get sort of brushed to one side in physics. You hear lectures about quantum field theory and relativistic quantum field theory. You've got this thing that we call quantum gravity. I remember one professor saying on a YouTube video, and then there are philosophical considerations. Like, whoa, what do you mean philosophical considerations? I mean, well, for one thing, physics is still part of philosophy. It's like saying that there's quantum gravity, which is a theory that we want, but then there's other stuff to consider in philosophy, which physics is part of ultimately. Do you see what I mean? And we're just going to brush that to one side because there's way more stuff to think about when it comes to quantum gravity. And it's part of these drawing of unnecessary lines between things and chopping things up and parceling things together in neat and, either unnecessarily abstruse or unnecessarily protracted mathematical forms when they could be more succinct, more put together, more elegantly and more neatly, I think. And I've gone for a lot of confusion really in my time as to whether or not my position within all this, since I felt this great impetus to try and solve this problem in myself, was towards the philosophical side or to the physical side of it, to the scientific side as opposed to the philosophical side of it. But really, they meet on the same point. What we're trying to do is find the next best model that integrates our best understandings of gravity and all fundamental forces ultimately, really, and tries to give explanations of those to audiences. So, audiences, in lecture theatres at universities, right, or to the public, or to whoever, to people on YouTube, right, even. It's or in written form, or in whatever form it happens to be. So the way I would go about it is saying we're looking for a quantum of a gravitational field. We're looking for a smallest unit of a gravitational field that we can't divide any further. Okay, so it's an indivisible unit, obviously. Where should we really be going looking for such a particle? Really, we should be going looking in the agglomeration of particles that we have already at the moment, I think, the standard model of particle physics. And the one that jumps out to me, and has always jumped out to me, is the electron as being a deeply important particle in gravity, since when it comes to gravitational fields, as I've mentioned with Einstein rings and these black hole firewalls, we're looking for a particle when en masse with loads of other electrons is capable of trapping vast quantities of light and giving rise to these macroscopic phenomena that we see in nature, of light being curved around galaxies and light being trapped in firewalls, or even around the corona of stars, right? So our sun and all other main sequence stars have corona surrounding them. All stars have corona surrounding them. It's sort of like the atmosphere of a star, whereby gas, dust, rock as well, probably, which is getting vaporized therein, along with the energy, the radiation, is also getting trapped there. So that presents, I think, an interesting sort of piece of evidence, really, that something that readily interacts with light particles, some quantum that likes to interact with photons, likes to interact with photons, it's just part of its behavior that it interacts with photons readily, the electron, is is playing a very important role in creating those phenomena. And that is my conviction. I believe that this is, it's an idea that was first teased out, or started getting teased out in the 18th century by Nicolas Fatio de Douillet, and later by Lesage, who believed he came up with a different version of the same theory, but may have been taught it as a child and he had memory problems and so on, apparently. And he espoused the same idea of a particle basis for gravitational fields, except they described their shadow gravity, as they called it, as flows of particles around massive objects, where really, more in line with B.L. Hughes' thinking, the particles of gravity are stochastic. It's more like they're randomly appearing and disappearing, but on a sort of, in the sense of them being virtual particles, they form an electron density surrounding massive objects, and while they're in a certain period of position in space, because of all the other particles around them, they move in classical space as well, along macroscopic vectors, if you like, directions in space. So if the Earth rotates, the electron density bound to the Earth will rotate as well. All those electrons will rotate in synchronization with the Earth's rotation. And we have this phenomena then of them being more likely to bounce into electrons from any electron density onto which the Earth's electron density has been superimposed. So you get a solution to the problem of dark matter this way, and the perihelion precession of Mercury. Mercury's perihelion precession, that is caused by gravitational waves coming from the sun, but also the lack of rotation of Mercury as a planetary body, that plays into things as well. That causes Mercury to be less stable in its orbit and more susceptible to these gravitational waves coming from the sun, if you see what I mean. The gravitational waves themselves coming from the sun, those might just be waves really of photons that get emitted, as a consequence of its wobble with the background. It might just emit large amounts of photons really in one particular area. Likewise, two black holes slamming into one another, those might just be photons, which in turn affect the background electron density, cause a little judder, a little spike in the background electron density, so we detect it at LIGO and things like this. And what we're talking about very, very minute periods of time that each electron appears within the electron density of, say, an object like the Earth. It would appear there for once every Planck second before it interacts with another photon again and disappears to a different part of the universe, whereupon it's replaced by yet another electron. And these sorts of considerations fall out of this sort of thinking. This is very, very, what's the best word to describe it? It's highly involved. It's a difficult idea to wrap your head around. But I like to think that something very intuitive falls out of it. I think what falls out of it really is it's the same force keeping the electron in orbit around the proton of a hydrogen atom as it is keeping the moon in orbit around the Earth. That's ultimately the image we get out of it, although it's not quite that simple. And atoms in their own right can be thought of as kind of like little planets, with the proton being the core of the planet, the outer electron density being sort of like the surface, and then there's an invisible part that we can't see further beyond that, which is more like the gravitational field of an atom. And the atom's gravitational field never tapers off to exactly zero. It never exhibits zero gravity. Well, that's debate. Well, that's the essence of the debate, really. The quantum theorists want to really say that it falls off to such a negligible small number, and this is what they've gotten wrong, what they have to have gotten wrong in quantum theory, as opposed to general relativity. As to such a small number, it falls off that it's practically impossible. It's practically impossible that an electron from a given atom will tunnel astronomical distances. But then you need to consider all the electrons in something like the Earth, the fact that they're tunneling once every Planck time, and start multiplying those sorts of numbers together, and then you do get a very small likelihood of any electron tunneling a very great distance, but it does, it's not the exponential function that's governing. It's not this perfect, harmonious, mathematically beautiful thing, or whatever you have in your heads. It's something else, really. It's a probability of the electron tunneling beyond the van der Waals radius of about 1 over 4.17 times 10 to the 42nd power, which gives a cutoff like that. It gives a curve. It gives something more akin to Newtonian gravity, though, the Newtonian gravity curve, which, I mean, if you want quantum gravity at all, you have to just accept that. You just have to accept that the atoms, really, are going to behave as Newtonianly gravitating objects, and that some quantum, probably the electron, let's face it, is causing, certainly the electron, I would say it's certainly the electron at this point, causing them to gravitate. And it's certainly the electron from one atom tunneling to within the electroweak range of the proton in another atom and exerting a force of gravity over its nucleus via the exchange of W plus and W minus particles. And those W plus and W minus particles, the mutual attraction between the W plus and the W minus cancels out the masses of the two particles, because they're mutually attracted to one another, so they feel there's nothing resistance in space between them. Creates a massless spin 2 gauge field, since they each have a spin of 1, which is what we predicted the graviton to be anyway. And the Weinberg-Witten theorem, it has some merit, since that is one graviton. That W plus and W minus thing, that's the attractive graviton, but there's also the resistive graviton, which is the photon, and that is a single particle, but it's a spin 1 particle, not a spin 2 particle. So, and it does have mass, unfortunately, as well. So the Weinberg-Witten theorem, also these are sub-relativistic scales. Emergent quantum gravity is a very, very respectable idea in quantum gravity research, one that I hold in very high regard. I think emergent gravity is certainly the truth. I think the phenomena of general relativity arises as an emergent phenomena out of many, many small quantum scale exchanges of particles occurring over Planck lengths and Planck times. These minutest scales in nature, very, very rapidly, way beyond our sense perceptions of reality, really beyond our measuring instruments as well and their capabilities, since we're down to attosecond physics at the moment, being able to glean those sorts of processes happening over attoseconds, but we're not down to Planck seconds quite by any stretch of the imagination. And these things are happening very, 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 very quickly. And I don't quite know what else I want to say about this, but it was just a set of concerns I'd like to raise, really, about the whole project of quantum gravity in general. Like there are philosophical considerations. What do you mean there are philosophical considerations? The whole thing is a philosophical consideration, and people would love to lurch out of the undergrowth and say you're just a charlatan pretending to be a physicist or whatever it is. Like, well, I'm a philosopher pretending to be a physicist, so there you go. Or I'm a philosopher of science, a philosopher of quantum gravity. I a cosmologist, I a sort of physicist as well, and it kind of blends into one thing, which is really the syncretism we're after, even with quantum gravity. Is it the electrical force, strong, weak, nuclear? They're all kind of the same force. It's all kind of, is gravity electromagnetism, gravito-electromagnetism, or gravito-electroweak theory, or gravito-electroweak strong, or whatever you want to call it. It all just kind of smushes in together. And really what we're doing with the standard model at the moment is that we're trying to see what we can get out of it to make it more elegant. I think one of the things we can get out of it is the gluon. I don't think we have any need of gluons. Perhaps on a level we can abandon up, down, top, bottom quarks if we consider those quarks to have a higher content of some W particle, say. Say for instance the top quark might have more than one W particle as opposed to the up quark, which is confusingly named enough, isn't it? Top and up versus, you know what I mean. We might be likewise with neutrinos, likewise with electrons, we might just skirt it down to like four really fundamental fermions. And yeah, 4 gauge bosons, so it'd be an 8-fold path again. No, without the gluon, so it'd be 7. 7. 7. I like the number 7. It's a great number. It's a lucky number. Maybe it should be the 7-fold path. An ultimate 7-dimensionality to nature. That's really interesting. I haven't really thought of this before. This is stuff I've just started thinking about, or really just started toying around with, like this idea that the muon, for instance, could be an electron just containing another W. Like a Matryoshka doll. I mean, the muon isn't really a fundamental particle, it's a composite particle. The fundamental particle is really the electron. It could be a 7. I could rewrite the whole standard model. I'm going to go away and try and do that. See you later, everybody.